morning dear friends. In the last session we have seen construction and working of metal oxide silicon field effect transistor, especially signal metal oxide silicon field effect transistor and power metal oxide silicon field effect transistor. Also we have seen what will be the difference between power MOSFET and the normal signal MOSFET. In this session we are going to learn the different characteristics of the power MOSFET, especially transfer characteristics, output characteristics, switching characteristics, and also the difference between power BJT and the power MOSFET. First, let's see the transfer characteristics of the power MOSFET. So we have seen the similar circuit when we learned the power BJT. Instead of BJT, we have replaced with the NPN metal oxide silicon field effect transistor. So we have drain, this is source, and the gate. We have seen this is NPN. That's why current is flowing from south to the current is flowing from source to drain. So let us see the transfer characteristics, how it will be work. For drawing the transfer characteristics, power is transferring, right? So when the power will be transferred, that's why it is called as transfer characteristics. For that, x-axis will be the gate source voltage. Why? The gate source voltage will control the power flow. That's why x-axis will be gate source voltage and y-axis will be the drain current. So based on the flow, based on the gate source voltage, we will control the electron flow. Automatically there will be the flow control of power, or otherwise there will be a control of drain current. So when we see here, when this gate source voltage is 0, automatically the drain current is also 0. So whenever this will start, whenever this is start to increase, this will start to increase, gate source voltage start to increase, still ID is continuously remains 0. Once this gate source voltage reaches gate threshold voltage or BGST, this ID current will start to increase. So normally the current is flows from source to drain, but for our commonly we used to draw the curve, draw the current ID. That's why we are referring only the ID, right? So now at this gate threshold voltage, then when this gate source voltage reaches threshold value, ID will start to increase further. So as long as when increase this gate threshold voltage further, ID will increase. So this is the characteristics of the transfer characteristics of the metal oxide silicon field effect transistor. So then second one, the typical value of the gate threshold value will be 2 to 3 volt. Maximum of 3 volt and minimum of 2 volt. So when we apply gate voltage less than 3 volt, this MOSFET will not conduct. So we have to apply the voltage more than the threshold value of 2 to 3 volt. Then let's see about output characteristics of the power MOSFET. In this output characteristics of the power MOSFET, if you see here, output in the sense output voltage. Voltage is voltage across drain to source, and current will be ID, drain current, right? So assume that when this drain to source voltage is very less, the variation of drain current with respect to drain source voltage is linear. See here, this is linear. Whenever the drain to source voltage is very less, this drain to source variation of drain current with respect to drain to source voltage is linear. The reason behind this is this normally this current flowing that resistance voltage, the path of the drain current is normally resistive in nature when drain to source voltage is very less. That's why we are getting the linear curve for various value, increasing the gate source voltage. When we, as long as we are increasing the voltage, automatically we will have increasing the value of ID. Increasing the value of ID, but VDC is very less. That time we will see the linear characteristics of the ID due to the resistance of the drain. Then once this drain source voltage increases further, we will see the constant voltage, the constant current. Current will be constant. Drain current will be constant. So for various values of increasing the value of when we increase the value of VGS, we can see the ID magnitude is increasing, at the same time it is constant for various values of VDS. So there is having two operating point A and B. A is called, you can see here, ID is maximum, right? ID is maximum, voltage is minimum. Then here VDS, this is maximum. The B operating point B is voltage is maximum, current is 0. So what we can say, it will block the forward voltage VDS maximum. That's why in this ideal characteristics of the power MOSFET also, VDS is maximum. VDS is maximum. Similarly, we cannot draw no need to draw the reverse voltage characteristics, but this the MOSFET will also block the drain source voltage in the reverse bias. When the polarity is reversed, it will block the reverse voltage as well. So now here we can see the voltage is less but the current is maximum. Ideally we can see current is maximum. So drain to source current is maximum. So that means IDS will not goes to negative. That means it is not bidirectional. It is only unidirectional. So the characteristics, ideal characteristics of the power MOSFET is same as the ideal characteristics of the bipolar junction transistor, right? So now in between this operating point A and B, this power MOSFET will act as a switch. So when this operating point moves to A, it will be switch on. When this operating point moves to B, it will be switch off. So this power MOSFET will act as a switch between the operating point A and B. Then let's see about the switching characteristics of the power MOSFET. The switching characteristics of the power MOSFET, same circuit. So here we are having NPN MOSFET, N-channel MOSFET. This is not NPN, sorry, N-channel MOSFET. So in this N-channel MOSFET, drain, source and gate. So the drain, source and gate, let me correct it now itself. So cannot correct. So I hope you understand. This is N-channel MOSFET. So drain, source and gate. Then we have connected through the drain resistance. Similarly, gate also connected. The same circuit which I have explained already. Already we know VGS. So now we have to apply gate voltage, right? We have to apply the gate voltage. Now we have applied the gate voltage, the magnitude of V1. This will be maximum. Gate voltage is maximum till T1. So I hope you understand why I have drawn this curve. So now when we apply this gate voltage, at the same time this gate source voltage will not increase suddenly. There is having a capacity effect. So the capacitor will start to voltage across the capacitor will start to increase. So that's why once this VGS voltage reaches threshold value, that's what we have seen in the previous characteristics curve also. VGS should be reaches threshold value of VGST, then only drain current will flow. Same way we can see here till this once the VGS reaches the VGST, the drain current will start to increase. Drain current will start to increase. Till that drain current will be 0, right? Then once if we apply this VG further, this VGST will reach us to gate source voltage will reach us to VGSP. The VGSP is nothing but sufficient gate source voltage to drive the metal oxide silicon field effect transistor. So this VGSP is nothing but sufficient gate to source voltage to drive it is required to drive the MOSFET. So it will be reached till this. So when this gate source voltage reaches started to increase from VGST to VGSP, this ID will start to increase. So this time, rising time, that means when this ID current started to increase and reaches the maximum time interval between ID current started to increase and reaches the maximum value is called as rise time. So what is meant by TDN? TDN is nothing but turn on delay time. The turn on delay time is nothing but the time interval to increase the gate source voltage to reach the gate threshold voltage. During this time interval, that means during the turn on delay time, drain current will be always 0. So I hope you understood now. Then one particular time after this gate source voltage reaches to VGSP, it will goes to the maximum of V1. Maximum voltage will be reaches. So till at T1, what I have done? We have switch off the gate voltage. That means we removed the supply of the VGS. So therefore at T1 it will be 0. So when even though we have make it at T1 gate source voltage 0, it will not suddenly goes to 0. It is gradually it will come down. So VGSP, that means there is having a some charge. I will tell you after explaining entirely why we require TDN, TR, TDF and TF. Then fault time, what is meant by fault time? Fault time means nothing but the time interval between gate source voltage started to reduce from VGSP to VGST. So that is called as fault time. During fault time, drain current will start to reduce from maximum to 0. Then, so this total on time is nothing but this turn on delay time plus the rise time. So that is called as total turn on time. Let's see now what is mean by what will happen during the TDN. What is TDN? Turn on delay time. During turn on delay time, input capacitance charges to VGST. I already told you there will be having a capacitive effect. So this VGS, once we give the voltage till the TDN, this input capacitance charges to VGST. So once the input capacitance charges to VGST, then only this MOSFET will start to conduct. Then what is meant by rise time? During the rise time, gate voltage will rises to VGSP. During the rise time, this gate source voltage will increases from VGST to VGSP. Then what is meant by turn off delay time? The turn off delay time is nothing but input capacitance discharge from V1 to VGSP. There is having the capacity effects already fully charged. Therefore, once we cut off the gate voltage, this capacitor voltage will start to reduce from V1 to VGSP. Then what is mean by fault time? The fault time is nothing but input capacitance discharge further from VGSP to VGST. So there is having one small mistake. Let me correct it here. This TDF and here it will be VGSP. So you can see now very clearly what is the difference between VGSP and there is no VGSPS. Okay, so now I hope you understand what is by on time. On time is nothing but delay time during on time plus rise time. So this is called as off time. Off time is nothing but this delay time during off time. Delay time during off time and then fault time. And so it is called as totally the off time. So this are all about the switching characteristics of the power MOSFET. Then let's see about the difference between power MOSFET and metal oxide silicon field effect transistor. As per the conduction, we already know power MOSFET is the current control device. Power BJT is the current control device. Power MOSFET is the voltage control device. Why power MOSFET is the current control device? there is no input impedance. Input impedance is very less in the bipolar junction transistor. Therefore, current will passes through the base. So that current is controlled. Here we are applying the voltage. As there is having insulating material, there will be the voltage only, it will increase. Current will be very less. That input impedance resistance is more. Therefore, it is voltage control device. Then switching speed. The power MOSFET is slow switching speed. So when in this power, so power BJT is slow switching speed, power MOSFET is fast switching speed. Why it is slow switching speed? After switching off, it needs some time to removal of charges in the base in the power MOSFET. That's why the time interval is required. More time is required to overcome the switching on to switching off, that time period. So that it is not suitable for high frequency application. So power MOSFET slow switching speed due to the base charges, base electrons we should remove it, right? Base electrons we should remove it. For that it needs some time. That we have already studied the switching characteristics and the characteristics as well. So that is why it is not suitable for high frequency application. So the power MOSFET fast switching speed, only the charges are there, only the charges, it will be removed very fast. So fast switching speed, then also suitable for high frequency application. High frequency nothing but high switching frequency applications. Then power MOSFET is having low input impedance. I already told you. That's why it is called as current control device. So power MOSFET will be high input impedance. So power BJT is low input impedance and power MOSFET is high input impedance. Then efficiency wise, low efficiency. What happened? There is having the high drop between high voltage drop between the collector to emitter due to the high resistance. So that the losses will be more, switching losses, therefore efficiency will be reduced. So, but in the power MOSFET, high efficiency due to on-state resistance is less. If the on-state resistance is less, the drops will be also less, therefore it is switching losses will be reduced, therefore it is having high efficiency. Then the complexity of driver circuit, as far as the power bipolar junction transistor is concerned, it required continuous base current to stay on state. So due to this, that we have to be do the complexity, the circuit design of driver circuit is having some complexity. At the same time, power MOSFET voltage only required, so that for maintaining the gate voltage constant, so that the complexity wise it is less. Then applications, as the bipolar junction transistor is applicable for low switching speed, it is applicable for motor controls especially. So low speed of switching and high current applications, we can use power MOSFET, especially motor control. So the power BJT. Power BJT is used for low speed switching and high current applications, especially motor control. Power MOSFET is already we know we can use for fast switching, therefore high speed switching applications we can use the power MOSFET. So it is normally used for DC to DC converters and power supplies applications. Then next one, last one, cost wise, power MOSFET is less expensive. The power bipolar junction transistor is less expensive than the power MOSFET. Power MOSFET is more expensive. So power MOSFET current control device, it has low switching speed, low input impedance, low efficiency, then it required continuous current, therefore it required complexity. It has the complexity of the driving circuit, and it is used for low speed applications and less expensive. As far as power MOSFET is concerned, voltage control device, it is applicable for fast switching application and it has high input impedance, therefore it is having also it has high efficiency due to the low on-state resistance, and voltage is only applied, so the complexity in the driver circuit is very less. It is applicable for high speed application, so DC to DC converters and power supply, and also the power MOSFET is more expensive. So with this we can conclude today's session. Next session we will learn about construction and working of insulated gate bipolar transistor.